Hello everybody and welcome to Nuclear Physics Lesson 5. Now in the last lesson we looked at two key definitions. We looked at the random nature of decay and we came up with the definition that it is impossible to predict exactly when an individual radioactive nucleus will decay, but it is possible to predict how many of a large radioactive sample will decay in a given time. And then we came up with the definition for half-life, which is the half-life of a radioactive substance is the time taken for half of the nuclei of a large sample to decay. Now in today's lesson we're going to be deriving the nuclear decay equation. Now as a bit of a warning now, this lesson is going to be quite heavy from a theory point of view and from a mathematical point of view. So this is the kind of lesson that I do suggest that you really take your time going through, make obviously detailed notes and try and work everything through with me as I go along. Obviously go back over it a few different times and really make sure that you understand some of the maths and some of the concepts that we're going to be covering in this lesson. So to start off today, I just want to remind you of the thought experiment that we did in the last lesson, because out of this thought experiment we can start to get some of the basics of what we're going to need in order to look at the decay equation itself. So on the screen on the left hand side I've just copied over the data from the last lesson from that DICE experiment. If you haven't watched that video for a while, I suggest just going back and reminding yourself of that before you come back and carry on this lesson. So let's just take the first roll then. We started with 100 dice and we said that if we rolled all of those, then the probability said that a sixth of those would roll a 1 and would therefore decay. So we said that 16 would, out of those 100, decay. So how did we work that out? Well, we said that we started with 100 dice and that the probability of decay was 1/6. So we took those 100 dice and we multiplied it by a sixth. Now mathematically at least, a sixth of 100 is 16 and 2/3. Obviously we did a little bit of rounding there, but we came up with that line in the last lesson. Now just from that equation there we can start to define some terms that we're going to start using later on. The 100 that we've got here I'm going to call big N, and we're going to call that the number of nuclei. And that's the number of nuclei at a given time. The next part was the probability of decay. Now the probability of decay we're going to give the symbol lambda, lowercase lambda, and that is known as the decay constant. Even though we've called it the decay constant is really just the probability of decay in a given time period. So we can therefore put a definition onto the decay constant. The decay constant is the probability of an individual nucleus decaying per unit time. Now because we've got the idea here of per unit time, that makes the decay constant have the unit of per second, or seconds to the -1. Of course, going back to number of nuclei, because that is a number and we're simply counting something, that doesn't have a unit, it is dimensionless. Finally then, for this line that we've got the 16 and 2/3, and that we are going to call capital A, where capital A is the activity. And therefore we can get the definition for activity, which says that the activity of a radioactive sample is the number of decays per second. Now we've got again this idea of per second. So from an SI point of view, the unit of activity will be per second, but we do actually now define a new unit, which takes the symbol capital B and lowercase q, and the name for that unit is becquerel. So BECQUEREL, named after Henri Becquerel, who was a French physicist. What we can see then, and the first equation that we've now derived for this lesson, is that the activity of a sample, the number of radioactive decays per second, is equal to the lambda, which is the decay constant, the probability of any individual nucleus decaying per second, multiplied by n, which is the number of nuclei that we've got at a given time. So I'm going to put that one in a red box as the first equation and the first key equation that we've derived in this lesson. We can now start to look properly at the decay equation. I will just bring the previous equation across. A is equal to lambda n. Now, while the activity tells us the number of radioactive decays per second, what we're interested in from the decay equation point of view is the rate of change of the number of radioactive nuclei that we have. Now, rate of change we know will always be d something divided by dt to start to use proper calculus notation, and we're interested in the rate of change of the number of nuclei or the number of radioactive nuclei in a particular sample. So therefore we can use the notation dn divided by dt. Now, of course, when it comes to rate of change, in the past we've tended in physics to use delta notation, say delta n divided by delta t. I'm not going to go into the differences between the delta notation that we've been using and the d notation that you tend to use in calculus, and obviously for those that have been doing differentiation and integration in maths, you'll have used exclusively the little d's in that notation, that calculus notation there. As I said though, I'm not going to go into the intricacies of calculus and why basically delta and d can be approximated to each other. That's way beyond A11, way beyond what we are trying to achieve today. So we'll leave that conversation alone. If you are really interested, you can go and have a look at that yourself in your own time. At this point then, we can plug into this equation the idea that the rate of change of the number of nuclei that we've got left is somehow linked to the activity, because the activity is the number that are decaying per second. The only change that we need to make to this equation though is to put a negative sign in here. That negative sign tells us that n is decreasing. So the number of nuclei that we've got will always be going down, it will always be decreasing, and from the DICE experiment we saw that those numbers do decrease as time goes on. Plugging lambda n into that equation then, we can see that dn by dt is equal to minus lambda multiplied by n. At this stage then, I'm going to rearrange this equation so that all the n's are on one side of the equation and anything not to do with n is on the other side of the equation. The first thing then is I'm going to divide both sides by n, and then I will multiply both sides by dt. What we get from that then is 1 over n, okay, there's our divided by n, multiplied by dn is equal to minus lambda dt. At this point then we are into some proper calculus, and what I'm going to do is I'm going to integrate both sides of the equation. So the integral of 1 over n dn is equal to the integral of minus lambda dt. Now, for those of you who are familiar with integration, you'll obviously be following this quite well. If you're not familiar with integration yet, try and follow it the best you can. You will come across it in maths at some point, and you might be able to then come back to this lesson and understand it a lot more. Now, the first thing we're going to do is to point out that on this side, minus and lambda are both constants, and therefore we can bring them outside the integral sign. What we've got then is that the integral of 1 over n dn is equal to minus lambda, they're constants, so we leave them alone, multiplied by the integral of dt. Now, just writing the integral of dt, it's implying that we're integrating the number 1. Yeah, I'll leave it in there for now just to see exactly what we're doing. Okay, now before we actually do this integral, we do need to put some limits onto our integral, because I want to do a definite integral rather than an indefinite integral to remove any random constants appearing in this derivation. If we go back to, again, last lesson, we know that we defined at time is equal to 0, so when we had 0 rolls or 0 time, we had an initial number of nuclei that we called n0. Sometime t later, and that can now be any time later, any number of rolls in the dice experiment, or any random time when it comes to nuclear decay, we're going to have a certain number n of nuclei remaining, and it's really that n that I've just written in red that we want to try and get an equation in order to work out, in order to calculate. If we now move that onto a fresh slide, then we're now in the position to do this integration. Now, the integral of 1 over n dn will equal the natural log of n. So if we now do the integral on the left hand side with the limits, we get the natural log of n from n0 to n. On the right hand side, the integral of 1 dt will just equal t. And therefore, when we take our limits into account, and obviously remember that we've kept that constant negative lambda out of the whole thing, we end up with t from 0 to t. Next stage then, we need to now expand with these limits. So on the left hand side, we end up with the natural log of n minus the natural log of n0. On the right hand side, we've still got minus lambda, and our limits say t minus 0. This stage, on the left hand side, we can apply one of our log rules and say that the natural log of a over b is natural log of a minus natural log of b. So if we work that backwards on the left hand side, we can see that what we have is the natural log of n divided by n0. On the right hand side, we'll multiply the brackets out. Obviously the 0 then becomes completely irrelevant to us, and what we're left with is minus lambda t. On to the next slide then. Our next stage is that we're going to apply the idea that e to the power of the natural log of x is equal to x, and that way we can raise both sides to the power of e, and we will be able to get rid of the natural log that's currently on the left hand side. So let's go ahead and do that. Obviously we're raising both sides of the equation as a power of e, so e to the natural log of n over n0 is equal to e to the minus lambda t. As we said with the rule in green on the left hand side, then basically the e and the natural log cancel each other out, and what we're left with is n over n0 is equal to e to the minus lambda t. Our final stage then is just to multiply both sides by n0, and what we're left with is n is equal to n0 e to the minus lambda t. And at that point I can put that into a red box, and that is now the decay equation. Before we move on and start to look at the decay equation and perhaps how to apply it, just a quick note about units. Both n and n0 are numbers, they are therefore dimensionless. With the e to the minus lambda t bit, whenever you have a power, whenever you have an exponent like that, the power itself has to be dimensionless. So when we look at lambda t, well, t has the unit of seconds. Lambda, the decay constant, has the unit of per second, and therefore the seconds and the per seconds in the exponent there cancel each other out. Lambda t itself, or lambda multiplied by t itself, is therefore also dimensionless. Now, for those of you that perhaps haven't come across this this number e before, e is known as Euler's number. It is sometimes called the natural number as well. It's an extremely important number in both maths and science, not just physics, but when you're looking at population growth in biology, e is an extremely important number. Now, it is an irrational number, so it's like pi. It doesn't repeat itself and it just goes on forever, but the first few digits of it at least are 2.71828 etc. I know it looks like it repeats at first, but after that 8 it does then carry on, and it has been proven that it is irrational. So we treat it like we would treat pi. It doesn't have a dimension, it is just a number, and we are using that number and then doing powers of it with the minus lambda t in this equation. So now hopefully we can tie the graph that we looked at last lesson, which is the exponential decay graph, we can tie that now nicely into the decay law that we've just derived. And that equation that you can now see on the screen is the equation that describes the graph that we have on the left hand side. If we now start to neaten it up a little bit, we can start to label the axis. So the x-axis, the horizontal axis, is our time axis measured in seconds, and our y-axis, our vertical axis, is n, the number of nuclei at that given time. This value here is n0, that is the number of nuclei when time is equal to 0. We've got two more things then to look at with the decay equation. Firstly then, I'm just going to remind ourselves of the equation that we have right at the start of the lesson. A is equal to lambda n, activity is equal to the decay constant, the probability of decay, multiplied by n, the number of nuclei that are remaining. What hopefully should be obvious from this equation then is that as n decreases, as we can see from the graph on the left hand side, A will also decrease, and it will decrease proportionally to n because lambda is a constant, so they will both decrease in the same way. Therefore, as n decreases exponentially, A, activity, will also decrease exponentially as well. If we take the decay equation then and multiply both sides by lambda, we can see that lambda n is equal to lambda n naught e to the minus lambda t. On the left hand side, lambda n we've already just defined as A. we can now say that lambda n naught is equal to a naught, the initial activity. And we can rewrite the decay equation then as A is equal to a naught e to the minus lambda t as well. So the activity will follow exactly the same shape. Yes, okay, the numbers are going to be different because activity and the number of nuclei are not necessarily, well, they're not measuring the same thing, but mathematically we can treat them very similarly. Finally then, for this lesson we need to somehow try to tie together the decay equation and half-life. Now if we go back to the definition of half-life, the half-life of a radioactive substance is the time taken for half of the nuclei of a large sample to decay. Now let's just bring back the decay equation. N is equal to n naught e to the minus lambda t. With the definition for half-life then, what it's saying is that when t is equal to the half-life, so when we've had a period of time elapsed that is equal to the half-life, the number of nuclei that we've got remaining will be the initial number of nuclei, n naught, divided by 2. So we've halved that initial number. We can plug these two values, therefore, on the right hand side into the decay equation on the left hand side. And we can come up with n naught over 2, so there's our substitution for n, is equal to n naught e to the minus lambda multiplied by t half-life. Okay, mathematically then, we've got n naught on both sides, so both of those cancel out. That leaves us with a half is equal to e to the minus lambda times the half-life. Now going back to the log law that we applied earlier, natural log of e to the x will equal x. We obviously had the idea that e to the natural log of x equals x earlier. What I've just written before is just the reverse of that. Therefore, if we take the log of both sides, natural log of a half is equal to minus lambda multiplied by the half-life. At this point, we just need another one of our log laws. So if we say natural log of a to the power of b is equal to b times the natural log of a. Okay, so that's just one of the other log laws that hopefully you'll have come across in maths. At this point then, we know that a half is the same as writing 2 to the power of minus 1. And therefore, natural log of 2 is equal to natural log of a half is equal to the natural log of 2 to the minus 1, which is the same, if we apply the log law on the right hand side, is the same as writing minus 1, so obviously you don't need to write the 1, minus the natural log of 2. So the natural log of a half is equal to minus the natural log of 2. Tidying this up then, minus natural log of 2 is equal to minus lambda times the half-life. The negative signs both sides will cancel out, and if we divide both sides by lambda, then what we're left with is that half-life is equal to the natural log of 2 divided by, divided by lambda, the decay constant, and that is our final key equation for the day. So at that point I'm going to end the lesson and we'll get straight on to our summary. We won't do any examples in this lesson. I'm going to leave that for the next video because that's been quite heavy on the theoretical side today, and in the next lesson I want to focus on the application of the decay law. Let's have a look at the equations though that we've looked at today. The first one is the activity equation. A is equal to lambda n, where A is the activity, lambda is the decay constant, the probability of a decay per unit time, and n is the number of nuclei that we have at a particular time. And there then on the screen are those two definitions. We then managed to derive the decay law, which is n is equal to n naught e to the minus lambda t. We also said that the activity will follow the same mathematical decay, that exponential decay, so A is equal to A naught e to the minus lambda t. And then finally we linked together half-life and decay constant, and we said that t half, the half-life, is the natural log of 2 over lambda. So as I said, that's it for this lesson. I do suggest that you go over that a few times and make sure that you get a lot of that quite heavy mathematics into your head. If you haven't got to that stage where you've done integration and natural logs and exponentials and all that kind of stuff in maths, then I suggest you just sort of almost take it as given that those are the equations. And as I said, in the next lesson we're going to move on and we're going to have a look at how we can apply those in more detail to some problems and to some approaches that we need to come up that we need to know about when it comes to solving problems to do with nuclear decay. So thank you very much, and I'll see you next lesson.